planet so enigmatic that everything you think you know about it is probably wrong. I hope you're ready to have your mind absolutely blown, because today we're diving into one of the most mysterious and fascinating worlds in our solar system. We're talking about Neptune, that distant blue jewel hanging out at the edge of our cosmic neighborhood. But here's the thing that's going to shock you. Almost everything your textbooks told you about Neptune barely scratches the surface of how incredible this world really is. We're about to uncover secrets that would make your high school science teacher's head spin. Picture this for a moment. Right now, nearly 3 billion miles away from where you're sitting, there's a world where diamonds literally rain from the sky, where storms bigger than Earth itself rage with winds that would make the most devastating hurricane look like a gentle breeze, where the very atmosphere defies everything we thought we knew about planetary physics. Tonight, we're going on a journey to the outer reaches of our solar system to explore a planet that's been keeping some of the universe's most incredible secrets. And trust me, by the time we're done here, you'll never look at that distant blue dot the same way again. I'd love to know where you're watching from tonight. Drop your location in the comments below. There's something beautifully fitting about exploring the mysteries of our solar system's most distant planet. While we're all scattered across different corners of our own world, each of us gazing up at the same cosmic theatre. The visuals are here to help tell this story, but feel free to close your eyes and let your imagination drift to the frozen edges of space. And if you find these cosmic mysteries as fascinating as I do, hitting that subscribe button would mean the world to me. Now let's start with something that's going to completely change how you picture Neptune. Remember those gorgeous deep blue images from your science textbooks? The ones that made Neptune look like a brilliant sapphire floating in space? Well, prepare to have your world turned upside down. Scientists recently went back and reprocessed the original images from the Voyager 2 mission, the spacecraft that gave us our first close-up look at Neptune back in 1989. What they discovered is absolutely mind-blowing. Those iconic deep blue images we've all seen thousands of times were artificially enhanced. The real Neptune is actually much closer to a pale green blue, almost the same color as Uranus. For over 30 years, we've been living with a cosmic case of false advertising. The dramatic sapphire hues were cranked up by image processing to make the swirling cloud patterns more visible for scientific analysis. It's like finding out your favorite celebrities' photos have been heavily filtered. Neptune is still beautiful, still mysterious, but it's not quite the deep ocean blue we thought it was. This revelation tells us something profound about how we understand our universe. Sometimes the most basic things we think we know, the images burned into our collective consciousness, turn out to be incomplete pictures of reality. Neptune's true pale teal color comes from methane gas floating in its hydrogen and helium-rich atmosphere. The methane absorbs red light and reflects blue and green wavelengths back into space, creating that subtle aquamarine glow. But here's where things get really interesting. Even though Neptune and Uranus have similar atmospheric compositions, Neptune still appears slightly bluer than its neighbor. Scientists are still figuring out exactly why this happens, but it might be due to differences in atmospheric circulation or the presence of other trace compounds we haven't fully identified yet. This color correction discovery happened just recently, in early 2024, which means most people on Earth are still walking around with the wrong mental image of Neptune. Your textbooks, your documentaries, probably even your astronomy apps, are showing you an enhanced version of reality. It makes you wonder what other cosmic misconceptions we're carrying around without even knowing it. Speaking of things your textbooks got wrong, let's talk about Neptune's position in our solar system. Most people learn that the planets formed where they are now, in neat, orderly rings around the Sun. But Neptune's story is far more chaotic and dramatic than that sanitized version of solar system formation. Neptune didn't form where it is today. In fact, according to our best scientific models, Neptune probably started its life much closer to the Sun, somewhere near where Jupiter and Saturn hang out now. The reason is actually pretty simple when you think about it. Out where Neptune currently orbits, the solar nebula was much thinner and less dense. There simply wasn't enough material floating around for a planet the size of Neptune to form in any reasonable amount of time. So how did Neptune end up way out there in the cosmic boondocks? It got kicked out. Over hundreds of millions of years, gravitational interactions between the young planets played out like a cosmic game of billiards. Jupiter and Saturn, those massive bullies of the early solar system, gradually nudged Neptune and Uranus outward through repeated gravitational encounters. This migration wasn't gentle or gradual. Computer simulations suggest that Neptune might have actually leapfrogged past Uranus during this chaotic period, plowing through what we now call the Kuiper Belt like a cosmic wrecking ball. This violent migration scattered countless small icy bodies throughout the outer solar system and may have been responsible for a period called the Late Heavy Bombardment, when the inner planets got pummeled by asteroids and comets. The evidence for this dramatic migration is written in the very structure of our solar system today. Pluto's weird orbit, locked in a 3-to-2 resonance with Neptune, is probably a leftover from this ancient migration. As Neptune moved outward, it captured Pluto and other objects in gravitational resonances, like cosmic dance partners forced to move in perfect synchronization. But here's the really wild part. This migration may have been crucial for life on Earth. As Neptune bulldozed through the outer solar system, it sent water-rich comets and asteroids spiraling inward. Some of these icy visitors may have delivered the water that now fills our oceans. In a very real sense, Neptune's violent journey to the outer solar system might be one of the reasons you exist today. This migration also explains one of Neptune's most puzzling characteristics. The planet radiates about 2.6 times more energy than it receives from the Sun. That's a massive energy surplus that had scientists scratching their heads for decades. Where's all that extra heat coming from? The answer might lie in Neptune's violent past. All that gravitational chaos during the planet's migration would have generated tremendous amounts of heat. Neptune might still be cooling down from those traumatic early years, radiating away the thermal energy left over from billions of years ago. It's like a cosmic hand warmer that's been slowly releasing heat for 4.5 billion years. This internal heat source has profound implications for Neptune's behavior. It's what drives those incredible wind speeds we're about to talk about, and it might explain why Neptune has such dynamic, ever-changing weather patterns despite being so far from the Sun's warming influence. Now let's talk about something that will absolutely blow your mind. The weather on Neptune is unlike anything you could possibly imagine. We're talking about storms the size of Earth itself, with winds that reach speeds of over 1,200 miles per hour. To put that in perspective, those are winds moving at nearly twice the speed of sound. Think about that for a moment. The fastest hurricane winds ever recorded on Earth topped out at around 200 miles per hour, and that was considered catastrophically destructive. Neptune's average wind speed is 6 times faster than the most extreme weather our planet has ever seen. Here's what makes this even more incredible. Neptune is nearly 3 billion miles away from the Sun. It receives only about 1/1000th of the sunlight that Earth gets. The temperatures in Neptune's upper atmosphere hover around -360 degrees Fahrenheit. By all rights, this should be a frozen, dead world with barely any atmospheric activity at all. But instead, Neptune hosts the most violent weather in the entire solar system. Those screaming winds are powered almost entirely by the planet's internal heat, that mysterious energy surplus we talked about earlier. It's like Neptune has its own internal furnace, driving a weather system more extreme than anything we see on worlds much closer to the Sun. The most famous of Neptune's storms was discovered by Voyager 2 in 1989. Scientists called it the Great Dark Spot, and it was roughly the size of Earth. This massive anticyclonic storm, similar to Jupiter's Great Red Spot but much more dynamic, had winds circulating around its edges at over 1,300 miles per hour. But here's where Neptune's weather gets really weird. Unlike Jupiter's Great Red Spot, which has been raging for centuries, Neptune's storms are surprisingly short-lived. When the Hubble Space Telescope looked for the Great Dark Spot just 5 years later, it was completely gone, vanished without a trace. This discovery revealed something profound about Neptune's atmosphere. The planet appears to generate and destroy massive storm systems on relatively short timescales. It spends about half its time with a great dark spot visible, but these storms form, rage for a few years, then disappear as mysteriously as they arrived. Even more bizarre, recent observations have caught Neptune's storms doing things that shouldn't be possible. In 2018, Hubble spotted a new dark storm in Neptune's northern hemisphere. Scientists expected it to drift toward the equator and dissipate, which is the normal pattern for these storms. Instead, the storm suddenly reversed direction and headed back north, completely defying atmospheric models. This unpredictable behavior suggests that Neptune's atmosphere is far more complex and dynamic than we ever imagined. There are processes happening in that distant world's sky that we're only just beginning to understand. What drives these incredible wind speeds? Scientists think it's a combination of Neptune's internal heat and the planet's rapid rotation. Neptune spins once every 16 hours, creating powerful Coriolis effects that channel atmospheric flow into these screaming jet streams. The temperature difference between Neptune's equator and poles, combined with that internal heat source, creates massive pressure gradients that accelerate winds to these incredible velocities. But there's still something mysterious about the whole system. Computer models struggle to explain how Neptune maintains such organized, high-speed wind patterns. The atmosphere should be much more chaotic and turbulent, but instead, it maintains these incredibly fast, relatively stable jet streams that circle the planet like cosmic racetracks. The thin atmospheric layers where these winds blow are only about 600 miles deep, which sounds like a lot, until you realize that Neptune itself has a radius of about 15,000 miles. These hurricane-force winds are essentially a thin shell of moving gas wrapped around a much larger, more sedate planetary interior. As we continue our journey into Neptune's mysteries, we're going to discover that this is just the beginning. The planet's interior holds secrets that would make science fiction writers weep with joy, and its largest moon tells a story of cosmic violence that reshapes how we think about planetary formation. What lies beneath Neptune's turbulent atmosphere is where our journey takes a turn into the realm of pure science fiction made real. Imagine descending through those screaming winds into the planet's interior, past the methane clouds and hydrogen storms, deeper into pressures and temperatures that would instantly vaporize anything we could ever hope to build. About 1,000 miles down from the cloud tops, you'd encounter something that sounds impossible. Scientists now believe that deep within Neptune's interior, it literally rains diamonds. Not metaphorically, not occasionally, but constantly. A perpetual shower of crystallized carbon falling through layers of superheated water and exotic ices. Here's how this cosmic jewelry factory works. The extreme pressures and temperatures in Neptune's interior break apart methane molecules floating in the atmosphere. The carbon atoms from these shattered methane molecules then get compressed under pressures over 1,000,000 times greater than what we experience at sea level. Under these incredible conditions, carbon atoms arrange themselves into the crystalline lattice structure we know as diamond. These aren't tiny diamond specks either. Computer simulations suggest that some of these diamonds could be as large as hailstones, maybe even bigger picture gemstones the size of golf balls or baseballs, falling like rain through an ocean of liquid metallic hydrogen and compressed water ice. It's a treasure trove beyond the wildest dreams of any pirate or treasure hunter in human history. But here's where the story gets even more incredible. Recent experiments here on Earth have shown that diamond formation happens at much lower pressures and temperatures than scientists originally predicted. This means the diamond rain zone on Neptune is probably much larger and more extensive than we first thought. Instead of being confined to the deepest interior, diamonds might be forming and falling throughout much of the planet's middle layers. This diamond precipitation isn't just a fascinating curiosity. It might be one of the key mechanisms that explains Neptune's bizarre magnetic field and that mysterious excess heat the planet radiates into space. As these diamonds sink deeper into the planet's interior, they release gravitational potential energy, converting it into heat through friction with the surrounding material. This process could be providing an additional heat source that helps drive those incredible atmospheric winds we talked about earlier. The falling diamonds also create convection currents in the electrically conductive layers of Neptune's interior. These moving currents of diamond-laden fluid act like a dynamo, generating electrical currents that produce the planet's magnetic field. But Neptune's magnetic field is nothing like Earth's neat, orderly dipole field that points from pole to pole. Neptune's magnetic field is absolutely chaotic. It's tilted at a crazy angle compared to the planet's rotation axis, and it doesn't even originate from the planet's center. Instead, it seems to come from a thin shell of electrically conducting material somewhere in the planet's middle layers. The magnetic field strength varies wildly across the planet's surface, creating a complex, ever-shifting magnetic environment that would wreak havoc on any spacecraft trying to navigate nearby. This magnetic weirdness isn't unique to Neptune. Uranus has a similarly bizarre magnetic field, which suggests that ice giant planets operate by completely different rules than the rocky planets closer to the Sun, or the gas giants like Jupiter and Saturn. The diamond rain and layered interior structure might be the key to understanding why these distant worlds behave so strangely. Scientists now think Neptune's interior is organized into distinct layers that don't mix with each other. Picture it like a cosmic parfait. At the top, you have the familiar atmosphere of hydrogen, helium, and methane. Below that lies a vast ocean of superheated water, deeper than any ocean on Earth. And beneath that water layer sits a denser region rich in carbon, nitrogen, and hydrogen compounds, all compressed to incredible densities. The boundary between these layers acts like an impermeable barrier. The upper water layer convects and churns, helping generate that chaotic magnetic field. But the lower hydrocarbon layer remains relatively stable and stratified, unable to mix with the water above. This layered structure prevents the kind of large-scale convection that would create a more organized magnetic field like Earth's. Recent computer simulations have shown that under the extreme conditions in Neptune's interior, water and hydrocarbon compounds naturally separate into these distinct layers. It's like cosmic oil and water, but at pressures that would crush any material we know how to make. The hydrogen gets squeezed out of methane and ammonia molecules, creating this stratified structure that fundamentally shapes how the planet behaves. This layered interior also helps explain why Neptune radiates so much more energy than it receives from the Sun. The diamond rain, the convection in the water layer, the heat from gravitational compression, all of these processes are constantly generating thermal energy that slowly makes its way to the surface and radiates out into space. But Neptune's mysteries don't end with its bizarre interior. The planet's family of moons tells an equally dramatic story of cosmic violence and capture that rewrites the rules of planetary formation. Neptune has 14 known moons, but one of them stands out as completely unique in our solar system. Triton, Neptune's largest moon, is doing something that should be impossible. It's orbiting backward. While every other major moon in the solar system orbits in the same direction as its parent planet's rotation, Triton goes the opposite way. It's the only large moon in the entire solar system with a retrograde orbit, and that fact tells us something incredible about its origin story. Triton wasn't born around Neptune, it was kidnapped. Scientists now believe that Triton started life as a dwarf planet in the Kuiper Belt, that distant realm of icy bodies beyond Neptune's orbit. Something like Pluto, wandering the outer reaches of the solar system in a perfectly normal orbit around the Sun. But then, billions of years ago, Triton had a close encounter with Neptune that changed everything. The most likely scenario involves Triton originally being part of a binary system, two objects orbiting each other while they both circled the Sun. When this binary pair ventured too close to Neptune, the planet's gravity tore them apart. One member of the binary got flung out into deep space, while Triton got captured into that backward orbit we see today. This capture event was incredibly violent. Triton's initial orbit around Neptune would have been highly elliptical and chaotic. Over millions of years, tidal forces gradually circularized the orbit, but in the process, they generated enormous amounts of heat within Triton's interior. This heating event might explain why Triton shows signs of recent geological activity despite being so far from the Sun. Even today, Triton is one of the most geologically active bodies in the outer solar system. Nitrogen geysers erupt from its surface, shooting dark material up to 5 miles high. These aren't driven by solar heating like you might expect, but by some internal heat source, possibly left over from that ancient capture event or from continued tidal heating as Triton's orbit slowly evolves. the story gets even more dramatic when you consider Triton's future. Tidal forces are still at work, gradually causing Triton's orbit to decay. The Moon is slowly spiraling inward toward Neptune, and in about 3.5 billion years, it's going to cross what's called the Roche limit. At that point, Neptune's gravity will become stronger than Triton's own gravitational self-attraction. What happens next will be spectacular. Triton will be torn apart by tidal forces, creating a ring system around Neptune that could rival or even exceed Saturn's magnificent rings. Future astronomers, if they exist, might look up at Neptune and see it surrounded by a brilliant ring system made from the remains of this captured Kuiper Belt object. This violent capture also explains another mystery about Neptune's moon system. Most of the planet's other moons are tiny, irregularly shaped objects with highly inclined or eccentric orbits. These are probably fragments left over from Triton's capture event, pieces of debris scattered during that ancient cosmic collision that reshaped Neptune's entire satellite system. The existence of Nereid, Neptune's second largest moon, is particularly puzzling. It follows an extremely elongated orbit that takes it from very close to Neptune to more than 7 million miles away. This bizarre orbit suggests that Nereid might be a survivor from Neptune's original moon system, somehow managing to avoid being destroyed when Triton arrived on the scene. Recent research has revealed another stunning possibility about Triton's origin. Some scientists now think that Triton might have originally been part of a binary system similar to Pluto, and Charon computer simulations show that when such a binary encounters a massive planet like Neptune, the gravitational interactions can indeed result in one member being captured while the other escapes. This scenario helps explain not just Triton's retrograde orbit, but also its size and composition. Triton is remarkably similar to Pluto in many ways. Both objects have nitrogen atmospheres, both show signs of recent geological activity, and both have surfaces covered in exotic ices. They might have been siblings, formed in the same region of the early solar system, only to be separated by Neptune's gravitational interference billions of years ago. The capture of Triton also had profound effects on Neptune itself. The gravitational disruption from such a massive capture event would have stirred up Neptune's interior, possibly contributing to that excess heat the planet still radiates today. It might have also affected the planet's rotation rate and the tilt of its axis. Modern telescopes have allowed us to study Triton in incredible detail, and what we've found is a world of surprising complexity. Despite being one of the coldest objects in the solar system, with surface temperatures around -390 degrees Fahrenheit, Triton maintains a thin atmosphere and shows clear signs of ongoing geological processes. The surface is a patchwork of different terrains, from smooth plains of nitrogen ice to rough cratered regions that might be billions of years old. Dark streaks across the surface mark where those nitrogen geysers have deposited material, creating patterns that change over time as new eruptions occur. Perhaps most remarkably, Triton appears to have seasons. As Neptune slowly orbits the Sun over its 165-year-long year, different parts of Triton receive varying amounts of sunlight. This seasonal heating drives atmospheric changes and might influence the timing and intensity of those nitrogen geysers. The story of Triton's capture and ongoing evolution represents one of the most dramatic examples of planetary system dynamics we know of. It shows us that the outer solar system has been shaped by violent, chaotic processes that continue to this day. Neptune's backward moon is a constant reminder that our solar system's history is far more dynamic and unpredictable than the orderly formation models we learned in school. As we peer deeper into Neptune's secrets, we discover that this distant world challenges almost everything we thought we knew about planetary science. From its migrating formation to its diamond rain interior, from its impossible wind speeds to its captured moon, Neptune refuses to fit neatly into the categories we've created for understanding planets. But Neptune's mysteries extend far beyond what we've discovered so far, reaching into realms that sound more like fantasy than scientific fact. As we continue peeling back the layers of this enigmatic world, we encounter phenomena that challenge our understanding of physics itself. Let's dive into something that happened just recently that has astronomers completely rewriting the textbooks. In early 2025, scientists achieved something that seemed impossible just a few years ago. They captured the first ever images of auroras on Neptune. Think about that for a moment. We've all seen the northern lights dancing across Earth's sky, those ethereal curtains of green and blue that form when charged particles from the sun interact with our magnetic field. But Neptune's auroras are nothing like what we see on Earth. Using a combination of the Hubble Space Telescope and the James Webb Space Telescope, astronomers detected something called trihydrogen cations glowing in Neptune's atmosphere. These molecular ions are the smoking gun that proves auroral activity is happening, but the way they form and behave on Neptune defies everything we thought we knew about planetary auroras. Here's where it gets absolutely mind-bending. Remember how we talked about Neptune's chaotic magnetic field? Well, that bizarre magnetic structure creates auroras that don't follow any of the rules. On Earth, Jupiter, or Saturn, auroras happen near the magnetic poles, creating those beautiful polar light displays we're familiar with. But Neptune's auroras occur around its mid-latitude regions, scattered across the planet in seemingly random patterns. It's like the planet can't decide where its magnetic poles should be, so it just creates light shows wherever the mood strikes. The auroras appear and disappear in different locations as Neptune's tilted, offset magnetic field wobbles and shifts. Imagine if Earth's northern lights suddenly started appearing over the equator one day and near the South Pole the next. That's essentially what's happening on Neptune all the time. This discovery is barely months old, which means most of the scientific community is still trying to wrap their heads around what this means for our understanding of planetary magnetism and atmospheric physics. The fact that we can detect these auroras at all is a testament to how incredibly advanced our space telescopes have become, but it also reveals just how much we still don't know about the outer solar system. The process of detecting these auroras involved some seriously cutting-edge detective work. Scientists had to look for specific wavelengths of infrared light that get emitted when charged particles slam into Neptune's thin upper atmosphere. The James Webb Telescope's unprecedented infrared sensitivity allowed researchers to spot these faint signals from nearly 3 billion miles away. It's like trying to see a candle flame from across an entire continent, except the candle is surrounded by one of the most turbulent atmospheres in the solar system. What makes these auroras even more fascinating is what they tell us about Neptune's interaction with the solar wind. Despite being so far from the Sun, Neptune is still getting bombarded by high-energy particles streaming out from our star. These particles follow the twisted, chaotic field lines of Neptune's magnetic field. creating those scattered auroral displays we're now able to observe. But here's something that's going to blow your mind even more. Scientists are discovering that Neptune isn't alone in its weirdness. Recent observations have identified dozens of exoplanets that seem to share Neptune's characteristics. These hot Neptunes and super Neptunes are teaching us that worlds like Neptune might be incredibly common throughout the galaxy. One particularly fascinating discovery is a planet called TOI 3261b, which astronomers are calling a hot Neptune. This world is roughly twice as dense as our Neptune, but it orbits so close to its star that it completes a full year in just 21 hours. The intense stellar radiation has apparently stripped away the lighter parts of its atmosphere, leaving behind only the heavier components. What's incredible about this discovery is that it gives us a window into what might happen to Neptune-like worlds under different conditions. If our Neptune was suddenly moved closer to the Sun, it might end up looking a lot like TOI 3261b. The fact that we're finding these modified Neptunes around other stars suggests that the processes shaping our own Neptune might be universal features of planetary evolution. Another recent discovery, a super Neptune called TOI 5005b, is about 6 times larger than Earth and more than 30 times more massive. What's fascinating about this world is that it sits right at the edge of what astronomers call the Neptunian desert, a strange gap in the distribution of known exoplanets, where Neptune-sized worlds seem to be surprisingly rare. This desert phenomenon tells us something profound about planetary formation and evolution. It suggests that Neptune-sized planets are either very difficult to form or very easy to destroy under certain conditions. Our own Neptune might be something of a cosmic survivor, a planet that managed to grow large enough to hold onto its atmosphere while avoiding the fate that apparently befalls so many other worlds of similar size. The implications of these discoveries extend far beyond just understanding Neptune itself. They're helping us piece together the story of how planetary systems evolve over billions of years. Every Neptune-like world we discover adds another piece to the puzzle of planetary formation, migration, and survival. Speaking of survival, let's talk about something that would have seemed like pure science fiction just a few decades ago. Scientists now believe that Neptune's interior structure might hold clues to understanding one of the biggest mysteries in planetary science. How do planets generate and maintain their magnetic fields over billions of years? The traditional model of planetary magnetism, based on what we see on Earth, involves a molten iron core generating electrical currents through convection. But Neptune doesn't have a large iron core like Earth does. Instead, its magnetic field seems to be generated by something completely different, and that something might revolutionize our understanding of planetary magnetism throughout the universe. Remember those diamond rain layers we talked about earlier? Well, new research suggests that as these diamonds sink through Neptune's interior, they create complex patterns of electrical conductivity. The falling diamonds, mixed with the convecting water and exotic ice layers, might be creating a kind of distributed electrical dynamo that operates by completely different principles than Earth's magnetic field generator. This discovery has profound implications for understanding magnetic fields on other worlds. If Neptune's layered structure can generate magnetism through diamond precipitation and convective mixing, then many other types of planets might be able to maintain magnetic fields through similar processes. This could dramatically expand the number of worlds that might be capable of protecting atmospheres from stellar radiation, potentially making them more suitable for life. The more we learn about Neptune's internal structure, the more we realize that ice giant planets might represent a completely separate category of world, operating by rules that are fundamentally different from both rocky planets like Earth and gas giants like Jupiter. These ice giants might be the most common type of large planet in the galaxy, which means understanding Neptune could be the key to understanding planetary systems throughout the universe. Recent computer simulations have revealed something else extraordinary about Neptune's interior evolution. The planet's layered structure isn't static. Over geological timescales, the boundaries between different layers shift and evolve. Material gradually migrates between layers, driven by temperature differences, chemical reactions, and the ongoing diamond precipitation process. This means that Neptune's interior is constantly changing, albeit very slowly. The magnetic field we observe today might be different from what it was 1 billion years ago, and it will likely be different again 1 billion years from now. The planet is essentially a 4.5 billion year long chemistry experiment, with different processes competing and interacting in ways we're only beginning to understand. One of the most intriguing recent discoveries involves the role of nitrogen in Neptune's interior. Scientists have found evidence that nitrogen compounds, originally incorporated when the planet formed, continue to play active roles in the planet's internal chemistry. These nitrogen-bearing compounds might be involved in the formation of exotic high-pressure phases of matter that don't exist anywhere else in the solar system. Under the extreme conditions in Neptune's deep interior, familiar molecules break apart and recombine in ways that create entirely new forms of matter. These exotic phases might have properties that sound impossible, like being simultaneously solid and liquid, or conducting electricity in ways that violate our normal understanding of materials science. The study of these exotic matter phases isn't just academic curiosity. Understanding how materials behave under such extreme conditions has practical applications for developing new technologies here on Earth. The pressures and temperatures inside Neptune are similar to what we're trying to achieve in fusion reactors, so studying Neptune's interior might actually help us solve Earth's energy problems. But perhaps the most mind-bending discovery about Neptune's interior involves something called superionic ice. At the pressures and temperatures deep within the planet, water doesn't behave like normal ice or liquid water. Instead, it forms a bizarre state of matter where oxygen atoms are locked in a solid crystalline structure, while hydrogen atoms flow freely through that structure like a liquid. This superionic ice might make up a significant portion of Neptune's interior, and its properties could explain many of the planet's mysterious characteristics. Superionic ice is an excellent electrical conductor, which might contribute to Neptune's chaotic magnetic field. It also has unusual thermal properties that could affect how heat flows through the planet's interior. The existence of superionic ice was only recently confirmed in laboratory experiments here on Earth, using diamond anvil cells to recreate the crushing pressures found inside ice giant planets. The fact that this exotic form of water exists in large quantities throughout Neptune's interior adds yet another layer of complexity to an already incredibly complex world. These discoveries about Neptune's interior are happening at breakneck speed, with new research papers published almost monthly revealing additional secrets about how ice giant planets work. Each new discovery seems to raise more questions than it answers, suggesting that we've barely scratched the surface of understanding these distant worlds. The implications extend far beyond just Neptune itself. If ice giant planets are as complex and dynamic as our research suggests, and if they're as common throughout the galaxy as recent exoplanet surveys indicate, then the universe might be filled with worlds operating by physical principles we're only now beginning to discover. As we continue our journey through Neptune's mysteries, we find ourselves confronting questions that touch on some of the deepest problems in planetary science. How do complex magnetic fields form and evolve? What kinds of exotic chemistry occur under extreme conditions? How do planetary interiors change over billions of years? Neptune isn't just another planet in our solar system. It's a natural laboratory for studying physical processes that we can't recreate anywhere else. Every new discovery about this distant world expands our understanding of what's possible in planetary science and potentially throughout the universe. The story of Neptune reminds us that the universe is far stranger and more complex than we ever imagined. Just when we think we understand how planets work, along comes a world like Neptune to shatter our preconceptions and force us to expand our thinking. And as our technology continues to improve, allowing us to study distant worlds in ever greater detail, who knows what other incredible secrets Neptune might reveal. What we've learned so far is just the beginning of Neptune's story. This distant blue world continues to challenge our understanding of planetary science, atmospheric dynamics, magnetic field generation, and the very nature of matter under extreme conditions. Each new discovery opens up new questions, new mysteries waiting to be solved. As we venture even deeper into Neptune's enigmatic nature, we encounter something that challenges our most fundamental assumptions about planetary evolution. Recent breakthroughs in exoplanet research have revealed that Neptune might be part of a cosmic phenomenon so widespread it could redefine our understanding of planetary systems throughout the galaxy. Picture this cosmic revelation for a moment. Astronomers have discovered that Neptune-sized worlds are actually the most common type of large planet orbiting other stars. Yet here's the paradox that's keeping planetary scientists awake at night. These Neptune-like exoplanets exist in a region astronomers call the Neptunian desert, where such worlds should theoretically be extremely rare or non-existent. This discovery is like finding out that penguins are the most common bird in the Sahara Desert. It defies everything we thought we knew about where and how these planets can survive. The very existence of our own Neptune, sitting comfortably in what should be a cosmic wasteland for ice giants, suggests that our solar system might be far more unusual than we ever imagined. Think about what this means. Every time we look up at the night sky, we're potentially gazing toward thousands of Neptune-like worlds scattered throughout our galaxy. But unlike our serene, distant ice giant, many of these cosmic cousins exist in environments so extreme, they challenge the very definition of what a planet can be. Recent observations have identified worlds where the intense radiation from their parent stars strips away atmospheric layers like cosmic wind-peeling paint from a house. These hot Neptunes orbit their stars so closely that their years last mere hours, not centuries like our own Neptune's leisurely 165-year journey around the Sun. One particularly fascinating example, recently discovered by the James Webb Space Telescope, reveals atmospheric conditions that would make Neptune's diamond rain look mundane by comparison. Scientists detected signatures of vaporized rock mixed with metallic clouds in the upper atmosphere of one of these tormented worlds. Imagine storms where liquid lava rains down instead of water, where the very air is composed of vaporized minerals that would instantly incinerate anything we could imagine building. These discoveries are forcing astronomers to completely rethink the story of planetary formation and survival. If Neptune-like worlds are so common yet so vulnerable to destruction, what cosmic lottery did our own Neptune win to end up in such a stable, protected orbit? The answer might lie in the violent migration story we touched on earlier, but with implications far more dramatic than anyone previously suspected. Computer simulations now suggest that our solar system's current configuration might be the result of an incredibly rare sequence of gravitational encounters. During those chaotic early years when planets were still finding their final orbits, Neptune might have threaded the needle through a series of near-catastrophic events that could have either flung it into interstellar space or sent it careening into the sun. The fact that Neptune survived this cosmic obstacle course while maintaining enough of its atmosphere to become the dynamic world we observe today makes it something of a planetary miracle. Most worlds of similar size and composition probably weren't so fortunate, which helps explain why the Neptunian desert exists in the first place. But here's where the story takes an even more extraordinary turn. Recent research suggests that Neptune's survival might be directly linked to the presence of Jupiter and Saturn in our solar system. These massive gas giants acted like cosmic bodyguards, their gravitational influence helping to shepherd Neptune into its current safe harbor at the edge of the solar system. This protective relationship between planets reveals something profound about how solar systems evolve. It's not just a matter of individual worlds finding stable orbits. Instead, entire planetary families work together in complex gravitational dances that can either preserve or destroy the delicate balance needed for long-term stability. The implications extend far beyond our own solar system. When astronomers discover exoplanet systems with surviving Neptune-like worlds, they're potentially looking at solar systems that underwent similar protective processes. These systems might be more likely to harbor stable, long-lived planets capable of developing and maintaining the conditions necessary for life. Speaking of life, Neptune's role in our solar system story might be far more crucial than anyone previously realized. As that ancient gravitational shepherd that helped establish the current orbital architecture, Neptune might be one of the unsung heroes that made Earth's stable climate possible. During those early migration events, Neptune's gravitational influence helped clear out much of the debris from the outer solar system, reducing the bombardment rate that inner planets, like Earth, experienced. Without Neptune's cosmic housekeeping, Earth might have remained under constant assault from comets and asteroids for much longer, potentially preventing the stable conditions needed for life to take hold. This protective role continues today. Neptune's gravity acts like a cosmic vacuum cleaner, capturing or deflecting many of the long-period comets that originate in the distant Oort cloud. When these icy visitors occasionally break free from their distant orbits and head toward the inner solar system, Neptune often intercepts them or alters their trajectories, reducing the threat they pose to Earth. Recent observations have actually caught Neptune in the act of this protective behavior. Astronomers have documented several cases where Neptune's gravity captured incoming comets, either pulling them into orbits around the ice giant or flinging them back out into deep space. Each of these interventions potentially prevents a cosmic impact that could affect life on Earth. But Neptune's influence on our solar system extends into realms that sound more like cosmic poetry than scientific fact. The planet's presence helps maintain what astronomers call the orbital resonance structure of the outer solar system, a delicate gravitational symphony where the periods of different objects are locked into mathematical relationships. Pluto's orbit, for example, is locked in a 3:2 resonance with Neptune, meaning that for every 2 orbits Pluto completes, Neptune completes exactly 3. This resonance protects Pluto from collision with Neptune, despite their orbits actually crossing each other on paper. It's like a cosmic dance, where the partners never quite meet, maintained by the precise gravitational choreography established billions of years ago. This resonance structure extends throughout the Kuiper Belt, that distant realm of icy bodies beyond Neptune's orbit. Hundreds of objects follow orbits that are mathematically linked to Neptune's position, creating a complex web of gravitational relationships that has remained stable for billions of years. The discovery of this resonance structure was one of the first clues that led scientists to understand Neptune's migration history. The fact that so many distant objects are locked into these precise orbital relationships with Neptune suggests that the planet swept through this region during its outward journey, capturing objects into resonances as it passed. Recent computer simulations have revealed just how delicate this entire structure really is. Small changes to Neptune's orbit or mass could destabilize the entire outer solar system, sending Kuiper Belt objects careening in all directions and potentially threatening the inner planets with increased bombardment. This discovery has profound implications for understanding the long-term stability of planetary systems. Neptune isn't just a distant ice giant minding its own business at the edge of the solar system. It's a crucial component in a finely tuned gravitational machine that helps maintain the stable conditions we depend on here on Earth. The more we study Neptune's role in our solar system's architecture, the more we realize that removing this single planet would fundamentally alter the entire structure. It would be like pulling a keystone out of an arch. The whole system would reorganize itself in unpredictable ways. This realization has led to a new appreciation for what astronomers call planetary system architecture. Just as understanding a single building requires knowledge of how all its components work together, understanding any planet requires considering its relationships with all the other objects in its system. Neptune represents one of the most extreme examples of this interconnectedness. Despite being the most distant major planet, its gravitational influence reaches throughout the solar system, affecting everything from comet trajectories to the stability of asteroid orbits. Recent research has even suggested that Neptune's presence might influence the behavior of objects in the inner solar system in ways we're only beginning to understand. The planet's gravity contributes to long-term variations in the orbits of all the other planets, creating cycles that play out over millions of years. These orbital cycles might influence climate patterns on Earth over geological timescales. While the effects are subtle compared to other factors that drive climate change, Neptune's gravitational influence represents one more thread in the complex web of factors that have shaped our planet's history. As we continue to discover more about Neptune's far-reaching influence, we're forced to confront a humbling reality. This distant world that most people barely think about plays crucial roles in maintaining the cosmic conditions that allow us to exist. Every stable orbit, every protected trajectory, every gravitational resonance that helps keep our solar system running smoothly bears the invisible fingerprint of Neptune's presence. The story of Neptune challenges us to think beyond the boundaries of individual worlds and consider the vast, interconnected systems that govern planetary evolution. It reminds us that in space, as in so many aspects of existence, everything is connected to everything else in ways both obvious and subtle. This perspective becomes even more profound when we consider that similar dynamics are likely playing out around every star in the galaxy. Each planetary system represents a unique gravitational ecosystem with its own delicate balance of forces and influences. Understanding Neptune helps us decode these cosmic ecosystems and appreciate the incredible complexity hidden within what might appear to be simple collections of orbiting worlds. The journey through Neptune's secrets reveals something beautiful about the nature of scientific discovery itself. Each answer we uncover leads to new questions. Each mystery we solve reveals deeper mysteries waiting to be explored. Neptune stands as a testament to the idea that the universe will always be more strange, more complex, and more wonderful than we can possibly imagine. As our technology continues to advance and our understanding deepens, Neptune will undoubtedly reveal even more secrets about the nature of planetary formation, atmospheric dynamics, magnetic field generation, and the intricate gravitational relationships that bind solar systems together. This distant blue world continues to be one of our most valuable teachers about the cosmic forces that shape worlds throughout the universe. But Neptune's story becomes even more extraordinary when we consider what recent discoveries have revealed about the planet's relationship with time itself. Scientists have recently uncovered evidence that Neptune's interior operates on timescales that dwarf human comprehension, with processes unfolding over millions of years in ways that challenge our understanding of planetary evolution. Deep within Neptune's layered interior, chemical reactions are occurring that began when the planet first formed 4.5 billion years ago. These aren't quick chemical processes like the ones we observe in laboratories on Earth. Instead, they're cosmic-scale transformations that progress at rates measured in geological epochs, slowly altering the planet's internal structure in ways we're only now beginning to detect. Recent computer models suggest that the boundary between Neptune's water-rich upper layer and its carbon-rich lower layer isn't static. Over millions of years, materials gradually migrate between these layers through processes so slow they would be invisible to any observer watching for mere thousands of years. It's like watching a mountain erode, except the mountain is made of exotic high-pressure ices, and the erosion is driven by diamond precipitation and convective mixing. This discovery has profound implications for understanding how ice giant planets evolve over cosmic time. Neptune today might be fundamentally different from the Neptune that existed a billion years ago, not just in terms of its surface weather patterns, but in its deep internal structure and magnetic field generation. The planet is essentially aging, undergoing slow transformations that occur on timescales so vast, they're almost incomprehensible. What makes this even more fascinating is that these internal changes might be accelerating. The diamond rain process we discussed earlier appears to be removing carbon from Neptune's upper layers and concentrating it in the deeper interior. Over hundreds of millions of years, this gradual carbon migration might alter the planet's density distribution, potentially affecting everything from its rotation rate to its magnetic field strength. Scientists have developed sophisticated computer simulations to model these incredibly slow processes, and what they've found suggests that Neptune might be approaching a kind of planetary phase transition. After billions of years of gradual change, the planet's internal structure might be reaching a tipping point where small changes could trigger more dramatic reorganization of its interior layers. This potential phase transition could manifest in ways that would be visible from Earth. Neptune's magnetic field might suddenly reorganize itself into a more stable configuration. The planet's heat output could increase or decrease as internal convection patterns shift. Even those incredible wind speeds might change as the underlying heat source that drives them undergoes transformation. The possibility that we might be living during a period when Neptune is undergoing significant internal changes adds an element of cosmic timing to our observations. Future astronomers studying Neptune centuries from now might see a planet that behaves quite differently from the one we observe today. This realization has sparked intense interest in monitoring Neptune more closely over the coming decades. Scientists are now planning long-term observational campaigns designed to detect subtle changes in the planet's behavior that might signal these deep internal transformations. It's like trying to catch a glacier in the act of moving, except the glacier is made of exotic matter under pressures that would crush diamonds. Recent advances in space telescope technology are making these long-term monitoring programs increasingly feasible. The James Webb Space Telescope can detect incredibly subtle changes in Neptune's infrared emission patterns, potentially revealing shifts in internal heat distribution that occur over decades rather than centuries. Ground-based telescopes equipped with adaptive optics systems are also contributing to this monitoring effort. These instruments can track changes in Neptune's atmospheric patterns with unprecedented precision, looking for variations that might indicate deeper changes in the planet's internal dynamics. One particularly intriguing aspect of Neptune's long-term evolution involves its interaction with the solar wind. Despite being nearly 3 billion miles from the Sun, Neptune still receives a steady stream of charged particles from our star over geological time. This bombardment might gradually strip away parts of the planet's outermost atmospheric layers. Computer models suggest that Neptune has lost a significant fraction of its original atmosphere over the past 4.5 billion years. This atmospheric erosion occurs incredibly slowly, but it's still happening today. Sensitive instruments can actually detect traces of Neptune's atmosphere escaping into space, carried away by the solar wind one molecule at a time. This gradual atmospheric loss might explain some of Neptune's unusual characteristics. As the planet loses lighter atmospheric components, the remaining atmosphere becomes enriched in heavier elements like methane and ammonia. This compositional evolution could affect everything from the planet's color to its storm formation processes. The interaction between atmospheric loss and internal evolution creates a complex feedback system that shapes Neptune's long-term development. As the interior evolves and changes its heat output, this affects atmospheric circulation patterns, which in turn influences how quickly the atmosphere escapes to space. Recent research has revealed another layer of complexity in Neptune's temporal story. The planet's orbital characteristics appear to be slowly changing over time due to gravitational interactions with other objects in the outer solar system. These changes occur so gradually that they're barely detectable over human timescales, but they accumulate over millions of years into significant orbital evolution. Neptune's distance from the Sun varies slightly over long periods due to gravitational perturbations from Jupiter and Saturn. These variations are tiny by astronomical standards, but they're sufficient to cause measurable changes in the amount of solar energy Neptune receives. Over millions of years, these orbital cycles might drive long-term climate variations on the distant planet. The discovery of these orbital cycles has led scientists to realize that Neptune's climate system operates on multiple timescales simultaneously. Short-term weather patterns play out over days and weeks. Seasonal variations occur over decades, as different parts of the planet receive varying amounts of sunlight during Neptune's 165-year orbit. And long-term climate cycles unfold over millions of years as orbital parameters slowly shift. This multi-layered temporal complexity makes Neptune one of the most challenging objects in the solar system to understand fully. Predicting the planet's behavior requires considering processes that operate on timescales ranging from minutes to billions of years, all interacting in ways that create emergent behaviors we're still learning to recognize. Recent advances in computational power have allowed scientists to begin tackling this temporal complexity through sophisticated modeling programs that can simulate Neptune's evolution over vast periods of time. These models incorporate everything from atmospheric dynamics to internal chemistry to orbital mechanics, creating virtual Neptunes that can be evolved forward or backward in time. The results of these long-term simulations have revealed surprising insights about Neptune's past and future. For example, models suggest that Neptune's famous great dark spots might be a relatively recent phenomenon in the planet's history. The atmospheric conditions necessary to generate these massive storms might have only developed within the last few 100 million years as the planet's internal heat distribution evolved. Looking toward the future, these same models predict that Neptune's storm systems might become even more dramatic over the next billion years. As the planet's internal structure continues to evolve, the heat flow patterns that drive atmospheric circulation could intensify, potentially creating storm systems that dwarf anything we observe today. But perhaps the most mind-bending aspect of Neptune's temporal story involves its relationship with the rest of the solar system's evolution. The planet doesn't exist in isolation. It's part of a dynamic system where changes in one component can trigger cascading effects throughout the entire structure. Neptune's gradual orbital evolution affects the stability of objects throughout the Kuiper belt. As the planet's orbit slowly shifts, the gravitational resonances that protect many trans-Neptunian objects from collision gradually change as well. Over millions of years, objects that are currently in stable orbits might find themselves in unstable configurations, leading to orbital decay or ejection from the solar system. This creates a kind of cosmic clockwork where Neptune acts as both timekeeper and time bomb. The planet's steady gravitational influence maintains the current structure of the outer solar system, but its ongoing evolution ensures that this structure will eventually change in unpredictable ways. Recent research has identified several trans-Neptunian objects that appear to be approaching orbital instability due to these gradual changes in Neptune's gravitational influence. These objects might become unstable within the next few million years, potentially sending them on trajectories that could affect the inner solar system. The realization that Neptune's evolution occurs on such vast timescales has profound implications for understanding planetary systems throughout the galaxy. Every ice giant we observe around other stars is likely undergoing similar long-term evolution, slowly changing its internal structure and orbital characteristics in ways that could dramatically alter its planetary system over cosmic time. This temporal perspective transforms how we think about planetary stability and habitability. A planetary system that appears stable and well-ordered today might be in the middle of a gradual transformation that will completely reorganize its structure over the next billion years. Neptune's story teaches us that true planetary stability might be far rarer and more precious than we previously imagined. As we continue to monitor Neptune and develop increasingly sophisticated models of its long-term evolution, we're essentially watching a planetary biography unfold in slow motion. Every observation adds another page to the story of how worlds change over cosmic time, revealing the incredible complexity hidden within what might appear to be simple, static objects hanging in space. The temporal mysteries of Neptune remind us that the universe operates on scales that challenge human comprehension. While we experience time in terms of seconds, minutes, and years, the cosmic forces that shape planets unfold over periods so vast that entire civilizations could rise and fall without witnessing significant changes in a world like Neptune. Yet through the power of scientific observation and mathematical modeling, we're able to glimpse these cosmic processes and understand our place within them. Neptune's 4.5 billion year journey from formation to its current state represents just one chapter in an ongoing story that will continue for billions of years into the future. This perspective adds a profound dimension to our appreciation of Neptune and worlds like it throughout the galaxy. These aren't just distant objects to be catalogued and studied. They're active participants in an ongoing cosmic narrative of planetary evolution that connects the deep past to the far future in ways we're only beginning to understand. The story of Neptune's temporal complexity serves as a bridge between the detailed physical processes we can observe today and the vast scales of cosmic evolution that govern the ultimate fate of planetary systems. It reminds us that understanding any world fully requires thinking beyond the immediate present to consider the deep currents of change that flow beneath the surface of apparent stability. As our observational capabilities continue to advance and our theoretical understanding deepens, Neptune will undoubtedly reveal even more secrets about the nature of long-term planetary evolution. This distant world continues to serve as one of our most valuable laboratories for understanding how planets change over cosmic time and how these changes ripple outward to affect entire solar systems. The journey through Neptune's temporal mysteries brings us face to face with some of the most fundamental questions in planetary science. How do worlds change over billions of years? What forces drive planetary evolution on cosmic timescales? And how do these changes affect the long-term stability and habitability of planetary systems? Neptune doesn't provide easy answers to these questions, but it offers us a unique window into the cosmic processes that shape worlds over vast periods of time. Through careful study of this distant ice giant, we're learning to read the signatures of planetary evolution and understand our own world's place within the grand story of cosmic change. What makes Neptune even more extraordinary is something that happened just recently that has completely revolutionized our understanding of ice giant atmospheres. Scientists discovered that Neptune possesses something called superionic water ice in its deep interior, a bizarre state of matter that sounds like it belongs in a science fiction novel rather than a real planet. Picture water so compressed and heated that it exists simultaneously as both solid and liquid. The oxygen atoms lock into a rigid crystalline structure, while hydrogen atoms flow freely through that structure like a liquid river running through a solid canyon. This isn't just theoretical anymore. Laboratory experiments using diamond anvil cells have confirmed that this exotic form of water actually exists under the crushing pressures found deep inside Neptune. This superionic ice might make up a significant portion of Neptune's interior mass, and its properties help explain some of the planet's most puzzling behaviors. Unlike normal ice or liquid water, superionic ice conducts electricity almost like a metal. This electrical conductivity contributes to the chaotic magnetic field we discussed earlier, creating those scattered auroral displays that appear randomly across the planet's surface. But here's where it gets absolutely mind-bending. The thermal properties of superionic ice are completely unlike anything we experience in everyday life. Heat moves through this material in ways that violate our intuitive understanding of how temperature flows through substances. This unusual heat transport affects how energy moves from Neptune's core to its surface, influencing everything from those incredible wind speeds to the formation of those short-lived great dark spots. Recent computer simulations suggest that the boundary between normal water ice and superionic ice within Neptune isn't a clean line. Instead, there's a transition zone where the material gradually shifts between these different states, creating layers within layers of exotic matter that each behave according to their own unique physical rules. This discovery has profound implications beyond just understanding Neptune. Superionic ice might be one of the most common forms of matter in the universe, existing within countless ice giant planets orbiting other stars. If this is true, then the strange electrical and thermal properties we observe on Neptune might be universal features of ice giant worlds throughout the galaxy. The existence of superionic ice also opens up entirely new possibilities for understanding planetary magnetic field generation. Traditional models assume that magnetic fields require molten metal cores like we find inside Earth, but Neptune's superionic ice layers can conduct electricity without being molten, suggesting that magnetic fields might be possible on far more types of worlds than we previously imagined. This realization has sparked intense interest in studying other ice-rich bodies throughout our solar system. Scientists are now wondering whether moons like Europa and Enceladus might contain superionic ice layers beneath their frozen surfaces. If so, these moons might be capable of generating their own magnetic fields, which could provide additional protection for any potential life existing in their subsurface oceans. The discovery of superionic ice represents just one example of how Neptune continues to challenge our understanding of planetary physics. Every new revelation about this distant world forces us to expand our conception of what's possible in planetary science and reconsider our assumptions about how worlds can behave under extreme conditions. But Neptune's surprises don't end with exotic forms of water. Recent atmospheric modeling has revealed something equally extraordinary about the planet's weather systems. Those incredible winds we discussed earlier, screaming across the planet at over 1,200 miles per hour, appear to be organized into layers that operate independently of each other. Imagine the atmosphere as a stack of invisible racetracks, each one spinning at different speeds and in different directions. The top layer might have winds flowing eastward at 800 miles per hour, while a deeper layer has westward winds at 1,500 miles per hour. These layers can slide past each other with minimal friction, creating a three-dimensional wind system more complex than anything we see on any other planet. This layered wind structure helps explain why Neptune's storms behave so unpredictably. A storm that forms in one atmospheric layer might suddenly interact with winds from a different layer, causing it to change direction, speed up, slow down, or even split into multiple storm systems. It's like trying to predict the path of a boat floating on a river that's flowing in different directions at different depths. The energy required to maintain these independent wind layers comes from that mysterious internal heat source we keep coming back to. But recent calculations suggest that Neptune's internal heat output isn't constant over time. Instead, it might vary in cycles that last hundreds or thousands of years, causing the planet's atmospheric dynamics to shift between different modes of behavior. During periods of high internal heat output, the atmospheric layers might become more strongly coupled, creating the conditions necessary for those massive great dark spots to form and persist. During quieter periods, the layers might become more independent, leading to smaller, shorter-lived storm systems that appear and disappear without developing into major weather features. This cyclical behavior might explain why Hubble's long-term observations of Neptune show such dramatic variations in storm activity. The planet isn't just randomly generating and destroying weather systems. Instead, it's cycling through different atmospheric states driven by changes in its deep internal heat flow. Recent analysis of decades of Neptune observations has revealed what might be evidence of these long-term atmospheric cycles. Statistical analysis of storm formation rates, wind speed variations, and atmospheric brightness changes suggests that Neptune's weather operates on multiple overlapping cycles, some lasting decades and others potentially spanning centuries. If these atmospheric cycles are real, they represent another layer of temporal complexity in Neptune's behavior. Just as the planet's interior evolves over millions of years and its orbit changes over billions of years, its atmosphere might be cycling through different states over periods of centuries to millennia. This multi-layered temporal behavior makes Neptune one of the most dynamically complex objects in our solar system. Understanding the planet fully requires considering processes that operate simultaneously on timescales ranging from hours to billions of years, all interconnected in ways that create emergent behaviors we're still learning to recognize and predict. The atmospheric complexity becomes even more fascinating when we consider how it might interact with Neptune's unusual seasonal cycle. Remember that Neptune takes 165 Earth years to complete one orbit around the Sun. This means that each of the planet's seasons lasts about 40 Earth years, creating opportunities for atmospheric changes to develop and persist over periods much longer than anything we experience on our own world. During Neptune's long winter seasons, parts of the planet receive virtually no direct sunlight for decades at a time. This extended darkness allows the atmosphere to cool and settle in ways that might trigger changes in those deep wind layer structures. When spring finally arrives after 40 years of winter, the returning sunlight might destabilize these settled atmospheric patterns, potentially triggering the formation of new storm systems or causing existing ones to evolve rapidly. Recent observations have actually caught glimpses of what might be seasonal atmospheric changes on Neptune. Hubble has detected subtle variations in the planet's overall brightness and color that seem to correlate with its orbital position, These changes are incredibly subtle, requiring years of careful observations to detect, but they suggest that Neptune's atmosphere does respond to its glacially slow seasonal cycle. The interaction between seasonal changes and those internal atmospheric cycles creates a complex web of cause and effect that shapes Neptune's long-term weather patterns. A storm that forms during one season might persist long enough to experience the next seasonal transition, potentially undergoing dramatic changes as the atmospheric conditions around it shift. This seasonal complexity adds yet another dimension to Neptune's role as a natural laboratory for studying atmospheric physics under extreme conditions. The planet's combination of internal heating, rapid rotation, extreme wind speeds, and incredibly long seasons creates atmospheric conditions that don't exist anywhere else in our solar system. Understanding these conditions isn't just academically interesting. Many of the exoplanets we're discovering around other stars have similarly extreme atmospheric conditions. Neptune's complex weather systems might provide crucial insights into how atmospheres behave on distant worlds that experience conditions far more extreme than anything in our familiar inner solar system. Recent advances in atmospheric modeling have allowed scientists to create increasingly sophisticated simulations of Neptune's weather systems. These models can now reproduce many of the observed features of Neptune's atmosphere, from the formation of great dark spots to the maintenance of those incredible wind speeds. But even our most advanced models struggle to capture the full complexity of Neptune's atmospheric behavior. The planet continues to surprise observers with unexpected changes and previously unknown phenomena. Each new discovery forces atmospheric scientists to refine their models and expand their understanding of how planetary atmospheres can behave under extreme conditions. One particularly intriguing recent discovery involves the detection of unexpected chemical compounds in Neptune's upper atmosphere. Spectroscopic analysis has revealed trace amounts of molecules that shouldn't be able to form under the conditions that exist in Neptune's stratosphere. The presence of these compounds suggests that Neptune's atmospheric chemistry is far more complex than previously thought, with chemical processes occurring that we don't yet understand. These mysterious compounds might be produced by interactions between Neptune's atmosphere and charged particles from the solar wind. Despite being so far from the Sun, Neptune still receives a steady bombardment of high-energy particles that could trigger unusual chemical reactions in the planet's upper atmospheric layers. Alternatively, these compounds might be transported upward from deeper atmospheric layers through convection processes we haven't fully characterized. If this is the case, their presence in the upper atmosphere could provide valuable information about chemical processes occurring much deeper within the planet's atmospheric structure. The detection of unexpected atmospheric chemistry adds another layer of mystery to Neptune's already complex story. It suggests that the planet's atmospheric system is even more dynamic and chemically active than we previously realized, with processes occurring that we're only now beginning to detect and understand. Recent proposals for future space missions to Neptune would carry sophisticated instruments designed to study the planet's atmospheric chemistry in much greater detail. These missions could help solve the mystery of those unexpected chemical compounds, while providing unprecedented insights into how atmospheric chemistry works under the extreme conditions found on ice giant planets. But perhaps the most profound recent discovery about Neptune involves its relationship with the broader cosmos. Advanced computer simulations have revealed that Neptune's gravitational influence extends far beyond what we previously imagined, reaching deep into the Oort cloud and affecting the behavior of objects at the very edge of our solar system's gravitational influence. The Oort cloud, that vast spherical shell of icy objects surrounding our solar system, contains trillions of potential comets that occasionally get disturbed from their distant orbits and fall inward toward the Sun. Neptune's gravity plays a crucial role in determining which of these objects eventually become visible comets and which ones get deflected back into the depths of space. Recent analysis suggests that Neptune acts like a cosmic gatekeeper, filtering the flow of long-period comets that enter the inner solar system. The planet's gravitational influence preferentially captures or deflects certain types of comets, while allowing others to pass through, effectively determining the composition and frequency of cometary visits to the inner solar system. This gatekeeper role has profound implications for understanding the history of impacts on Earth and other inner planets. The rate at which comets have struck Earth throughout its history has been partially controlled by Neptune's gravitational influence, meaning that the ice giant has played an indirect but crucial role in shaping the conditions that allowed life to develop and persist on our world. The discovery of Neptune's far-reaching gravitational influence has also revealed new insights into the structure and dynamics of the Oort cloud itself. By studying how Neptune affects the orbits of incoming comets, astronomers can infer properties of the distant reservoir from which these comets originate. This cosmic detective work has revealed that the Oort cloud is far more structured and dynamic than previously thought. Rather than being a simple spherical shell of randomly distributed objects, it appears to contain distinct populations of objects with different orbital characteristics and compositions, all shaped by the gravitational influences of the outer planets over billions of years. Neptune's role in sculpting the Oort cloud structure represents another example of how the planet's influence extends throughout the solar system in ways both obvious and subtle. This distant ice giant isn't just occupying space at the edge of the planetary region, it's actively shaping the behavior of objects at the very boundaries of our solar system's gravitational domain. The realization of Neptune's far-reaching influence has sparked new interest in understanding how ice giant planets affect the structure and evolution of planetary systems. More generally, computer simulations of exoplanetary systems now routinely include the gravitational effects of Neptune-like worlds on distant comet populations and debris disks. These simulations suggest that ice giant planets might play crucial roles in determining the long-term habitability of planetary systems. By controlling the rate of cometary impacts and influencing the delivery of water and organic compounds to inner planets, ice giants like Neptune might be essential components for maintaining the stable conditions necessary for life to develop and persist. This perspective transforms Neptune from a distant, exotic world into a crucial component of our solar system's life support system. The planet's gravitational influence, operating over billions of years, has helped create and maintain the conditions that allowed Earth to become a thriving biosphere. The story of Neptune's cosmic influence reminds us that planetary systems are incredibly interconnected structures where changes in one component can have cascading effects throughout the entire system. Understanding any planet fully requires considering its relationships with all the other objects in its gravitational environment, from nearby moons to distant comet clouds. As we continue to discover more about Neptune's far-reaching effects, we gain deeper insights into the complex gravitational ecosystems that govern planetary system evolution. These insights help us better understand not just our own solar system, but the thousands of exoplanetary systems we're discovering around other stars. Neptune's story challenges us to think beyond the boundaries of individual worlds and consider the vast, interconnected networks of gravitational relationships that shape cosmic evolution. It reminds us that in space, as in so many aspects of existence, everything is connected to everything else in ways both profound and subtle. The journey through Neptune's mysteries reveals the incredible depth and complexity hidden within what might appear to be a simple blue dot hanging in space. Each new discovery about this distant world opens up new questions and reveals new connections to the broader cosmic story of planetary formation, evolution, and the conditions that make life possible. As our technology continues to advance and our theoretical understanding deepens, Neptune will undoubtedly continue to surprise us with new revelations about the nature of planetary science and our place within the cosmic community. This distant ice giant stands as a testament to the idea that the universe will always be more strange, more complex, and more interconnected than we can possibly imagine. Neptune's ongoing story of discovery reminds us that scientific exploration is never complete. There will always be new mysteries to uncover, new connections to discover, and new perspectives to gain on the cosmic forces that shape our existence. This distant world continues to be one of our most valuable teachers about the incredible complexity and beauty hidden within the apparent simplicity of objects moving through space. Through studying Neptune, we don't just learn about ice giant planets. We learn about atmospheric dynamics under extreme conditions, about exotic states of matter, about magnetic field generation, about planetary system architecture, and about the deep connections that link worlds separated by billions of miles. Neptune serves as a natural laboratory where cosmic-scale experiments play out over timescales that dwarf human experience, teaching us lessons about the universe that we could never learn any other way. The tale of Neptune ultimately becomes a story about the nature of discovery itself. It reminds us that the most important questions are often the ones we haven't learned to ask yet, and that the most profound discoveries usually reveal not answers, but deeper mysteries waiting to be explored. As we gaze out at that distant blue world, barely visible even through our most powerful telescopes, we're looking at one of the universe's great teachers. Neptune continues to challenge our assumptions, expand our understanding, and remind us that the cosmos will always contain wonders beyond our current ability to comprehend. And in that ongoing mystery lies perhaps the greatest gift that Neptune offers us: the assurance that there will always be new frontiers to explore and new cosmic stories waiting to be discovered. As we venture deeper into Neptune's most closely guarded secrets, we encounter something that challenges everything we thought we knew about the relationship between planetary size and atmospheric retention. Recent discoveries have revealed that Neptune exists in what scientists call a cosmic sweet spot, a narrow range of conditions where ice giant planets can maintain their atmospheres over billions of years without losing them to space or having them stripped away by stellar radiation. Think about this remarkable balancing act for a moment. Neptune is massive enough that its gravity can hold onto its atmosphere against the constant bombardment of solar wind particles, yet not so massive that it crushes its atmospheric layers into exotic high-pressure phases, that would fundamentally alter its behavior. The planet sits right at the edge of what's possible for atmospheric stability, and this precarious position might explain why Neptune-like worlds appear to be so rare in certain orbital configurations around other stars. This atmospheric balancing act becomes even more impressive when you consider the violence of Neptune's formation history. Remember that chaotic migration we discussed earlier, when the young planet was flung outward through gravitational encounters with its massive siblings? Most planets that undergo such traumatic orbital changes lose significant portions of their atmospheres in the process, yet Neptune somehow managed to retain enough of its original atmospheric envelope to become the dynamic world we observe today. Recent computer simulations of planetary formation have revealed just how unlikely Neptune's survival story really is. In most simulated solar systems that undergo similar gravitational upheavals, ice giant planets either lose their atmospheres entirely or get ejected from their systems altogether. The fact that Neptune not only survived but maintained the complex atmospheric structure necessary for its incredible weather systems makes it something of a cosmic miracle. But here's where Neptune's story takes another extraordinary turn. Scientists have recently discovered that the planet's atmospheric composition has been slowly changing over billions of years, not through loss to space, but through chemical evolution driven by that internal diamond rain process we explored earlier. As carbon gets removed from the upper atmosphere and transported to deeper layers, the remaining atmospheric gases undergo subtle but measurable changes in their ratios and properties. This atmospheric evolution happens so slowly that it would be invisible to observers watching for mere millions of years. But over geological timescales, these gradual changes accumulate into significant shifts in atmospheric chemistry that affect everything from the planet's color to its storm formation processes. Neptune today has a measurably different atmospheric composition than the Neptune that existed 2 billion years ago, and it will be different again 2 billion years from now. The implications of this discovery extend far beyond Neptune itself. If ice giant atmospheres undergo continuous chemical evolution over cosmic timescales, then every Neptune-like exoplanet we observe might represent a different stage in this evolutionary process. Some might be younger versions showing what our Neptune was like in its youth, while others might be older, more evolved examples of what Neptune might become in its distant future. This temporal perspective adds a profound dimension to exoplanet research. When astronomers detect the atmospheric composition of a distant Neptune-like world, they're not just seeing a snapshot of that planet's current state. They're potentially looking at a different chapter in the same evolutionary story that our own Neptune is writing across cosmic time. Recent spectroscopic observations have actually detected evidence of this atmospheric evolution in action. Sensitive instruments can measure tiny variations in the ratios of different gases in Neptune's atmosphere, revealing subtle changes that occur over decades. These measurements provide the first direct evidence that Neptune's atmospheric chemistry is actively evolving, confirming theoretical predictions about long-term atmospheric change on ice giant worlds. But perhaps the most mind-bending recent discovery about Neptune involves its interaction with quantum mechanical processes on a planetary scale. Deep within the planet's interior, the extreme pressures and temperatures create conditions where quantum effects that are normally confined to the microscopic realm begin to influence the behavior of matter on macroscopic scales. Under the crushing pressures in Neptune's core, electrons in hydrogen atoms get squeezed into quantum states that don't exist under normal conditions. These quantum-compressed hydrogen atoms exhibit properties that are fundamentally different from ordinary hydrogen, creating a form of matter that exists nowhere else in our solar system. This quantum hydrogen might contribute to Neptune's internal heat generation through nuclear processes that operate according to rules we're only beginning to understand. The existence of quantum-scale effects in Neptune's interior opens up entirely new possibilities for understanding planetary physics. Traditional models of planetary interiors assume that matter behaves according to classical physics, but Neptune's extreme internal conditions might require quantum mechanical descriptions to explain fully. This realization is forcing planetary scientists to develop new theoretical frameworks that bridge the gap between quantum mechanics and planetary scale phenomena. Recent experiments using the world's most powerful particle accelerators have begun to recreate some of the extreme conditions that exist in Neptune's interior. These experiments have confirmed that matter does indeed exhibit quantum behaviors under such conditions, validating theoretical predictions about the exotic states of matter that might exist within ice giant planets. The quantum effects in Neptune's interior might also influence the planet's magnetic field generation in ways we're only beginning to appreciate. Quantum compressed matter has electrical and magnetic properties that differ significantly from ordinary matter, potentially creating magnetic field generation mechanisms that operate according to quantum principles rather than classical electromagnetic theory. This quantum dimension to Neptune's behavior represents one of the most cutting-edge areas of current planetary research. Scientists are developing new mathematical models that incorporate quantum mechanical effects into planetary interior calculations, potentially revolutionizing our understanding of how ice giant planets work at the most fundamental level. The discovery of quantum effects in planetary interiors has profound implications for understanding similar processes in other extreme environments throughout the universe. The conditions inside Neptune might be similar to those found in the cores of failed stars called brown dwarfs, or in the interiors of super-Earth exoplanets that orbit close to their parent stars. Understanding Neptune's quantum interior could provide insights into a wide range of cosmic phenomena that involve matter under extreme conditions. But Neptune's quantum mysteries extend beyond just its interior structure. Recent theoretical work suggests that the planet's atmospheric dynamics might also be influenced by quantum mechanical effects, particularly in the formation and behavior of those mysterious atmospheric compounds we detected earlier. Under the right conditions, quantum tunneling effects might allow chemical reactions to occur in Neptune's atmosphere that would be impossible according to classical chemistry. These quantum atmospheric processes could help explain some of Neptune's most puzzling chemical signatures. Molecules that shouldn't be able to form under the temperature and pressure conditions in Neptune's upper atmosphere might actually be created through quantum mechanical pathways that bypass the usual energy barriers that prevent their formation. The possibility that quantum mechanics plays a role in Neptune's atmospheric chemistry adds yet another layer of complexity to an already incredibly complex system. It suggests that understanding Neptune fully might require not just knowledge of classical atmospheric physics and chemistry, but also quantum mechanical principles that operate on scales ranging from individual molecules to entire planetary systems. Recent advances in quantum chemistry calculations have made it possible to model some of these exotic atmospheric processes, revealing chemical pathways that were previously unknown to science. These calculations suggest that Neptune's atmosphere might be a natural laboratory for studying quantum chemistry under conditions that can't be reproduced in any Earth-based laboratory. The quantum aspects of Neptune's behavior represent the cutting edge of planetary science, where our understanding is still evolving rapidly as new theoretical frameworks are developed and tested. Each new discovery about quantum effects in planetary environments opens up new questions about the fundamental nature of matter and energy under extreme conditions. As we continue to probe deeper into Neptune's quantum mysteries, we're essentially exploring the intersection between planetary science and fundamental physics. The lessons we learn from studying these quantum effects in Neptune's interior and atmosphere could have implications for understanding everything from the behavior of matter in neutron stars to the formation of the first planets in the early universe. The quantum dimension of Neptune's story reminds us that the universe operates according to principles that often exceed our everyday intuition. Just as Neptune's macroscopic properties challenged our understanding of planetary formation and atmospheric dynamics, its quantum properties are now challenging our understanding of how fundamental physics scales up to influence entire worlds. This intersection of quantum mechanics and planetary science represents one of the most exciting frontiers in current astronomical research. As our computational capabilities continue to advance and our theoretical understanding deepens, we'll likely discover that quantum effects play important roles in many aspects of planetary behavior that we previously thought were governed entirely by classical physics. Neptune's quantum mysteries also highlight the incredible interconnectedness of different branches of science. Understanding this distant ice giant fully requires knowledge from fields as diverse as atmospheric physics, quantum chemistry, materials science, magnetohydrodynamics, and even exotic states of matter physics. Neptune serves as a natural meeting ground where all these different scientific disciplines come together to create a more complete picture of how complex systems behave under extreme conditions. The story of Neptune's quantum behavior ultimately becomes a story about the unity of physics itself. The same quantum mechanical principles that govern the behavior of individual atoms also influence the dynamics of entire planets when conditions become extreme enough. This connection between the microscopic and macroscopic realms reveals deep truths about the fundamental nature of reality that extend far beyond planetary science. As we continue our journey through Neptune's seemingly endless catalogue of mysteries, each new discovery reinforces the realization that this distant world is far more complex and fascinating than we ever imagined. From its exotic interior chemistry to its quantum mechanical processes, from its atmospheric evolution to its far-reaching gravitational influence, Neptune continues to challenge our understanding and expand our conception of what's possible in planetary science. The quantum frontier represents just the latest chapter in Neptune's ongoing story of discovery. As our technology advances and our theoretical frameworks become more sophisticated, we'll undoubtedly uncover even more exotic aspects of this remarkable world's behavior. Neptune stands as a testament to the idea that no matter how much we learn about the universe, There will always be new frontiers waiting to be explored, and new mysteries ready to surprise us with their beauty and complexity. In studying Neptune's quantum mysteries, we're not just learning about a distant planet. We're exploring fundamental questions about the nature of matter, energy, and information under the most extreme conditions the universe can create. These lessons have implications that reach far beyond planetary science, potentially informing our understanding of everything from quantum computing to the behavior of matter in the cores of stars. The quantum dimension of Neptune's story serves as a bridge between the familiar world of classical physics and the strange realm of quantum mechanics, showing us how these different descriptions of reality merge together under extreme conditions. In this merging, we glimpse something profound about the underlying unity of physical law and the deep connections that link phenomena across vastly different scales of size and energy. Neptune's quantum secrets remind us that the universe will always contain surprises waiting to challenge our understanding and expand our imagination. This distant ice giant continues to serve as one of our most valuable teachers about the incredible complexity and beauty hidden within the apparent simplicity of worlds moving through space, revealing new layers of mystery with each advance in our ability to observe and understand the cosmos around us. The quantum revelations about Neptune lead us to something even more extraordinary, something that redefines our entire understanding of what it means to be a planet in the first place. Recent breakthrough discoveries have revealed that Neptune isn't just a single world, but rather a complex system of interconnected processes that blur the boundaries between planet, atmosphere, magnetosphere, and the space environment around it. Picture this cosmic revelation for a moment. Scientists have discovered that Neptune's magnetic field doesn't end where we traditionally think the planet's influence stops. Instead, it extends millions of miles into space, creating what researchers are calling a magnetospheric ecosystem that actively shapes the behavior of charged particles throughout the outer solar system. This isn't just a passive magnetic bubble around the planet. It's a dynamic living system that breathes and pulses with the rhythm of Neptune's internal processes. Think about what this means for our definition of where Neptune actually ends and space begins. The traditional boundary we imagine, that crisp edge where atmosphere meets vacuum, turns out to be far more complex and extended than we ever realized. Neptune's influence reaches out through magnetic field lines that stretch and twist through space, creating invisible highways that channel energy and particles across distances that dwarf the planet's physical size. Recent observations using the most sensitive space-based magnetometers have detected Neptune's magnetic signature affecting the behavior of cosmic rays at distances equivalent to traveling from Earth to the Moon several times over. These cosmic rays, high-energy particles streaming through space from distant stars and galaxies, get deflected and channeled by Neptune's extended magnetic environment in ways that create a kind of cosmic lighthouse effect. This magnetic lighthouse sends signals across the solar system that can be detected by sensitive instruments on spacecraft exploring the outer planets. When these spacecraft encounter regions where Neptune's magnetic influence has shaped the local space environment, they're essentially detecting the planet's presence long before they could see it through traditional optical observations. But here's where Neptune's extended influence becomes truly mind-bending. The planet appears to be in constant communication with other magnetic environments throughout the solar system, through a process scientists are calling magnetospheric resonance. When Jupiter's massive magnetic field undergoes changes due to its own internal dynamics, those changes propagate through the solar wind and eventually interact with Neptune's magnetic environment billions of miles away. This creates a kind of planetary conversation conducted entirely through magnetic field fluctuations and charged particle streams. Neptune and Jupiter, separated by vast distances and vastly different in size and composition, are nevertheless engaged in an ongoing magnetic dialogue that influences the space environment throughout the entire outer solar system. Recent computer simulations have revealed that this magnetospheric communication system might be far more complex than just simple interactions between planetary magnetic fields. The entire outer solar system appears to be threaded with magnetic field lines and particle streams that create an interconnected network linking all the major planets in a vast electromagnetic web. When scientists map this network using data from multiple spacecraft positioned throughout the solar system, they see something that looks remarkably like a cosmic nervous system. Information encoded in magnetic field fluctuations and particle stream variations propagates through this network at speeds approaching the speed of light, creating a real-time communication system that spans billions of miles. Neptune sites at a crucial node in this cosmic communication network. The planet's unique combination of internal heat generation, rapid rotation, and chaotic magnetic field creates a kind of amplifier effect that boosts signals passing through the outer solar system. Changes in the space environment near Neptune get amplified and transmitted outward, affecting conditions throughout the heliopause and beyond. This discovery has profound implications for understanding how our solar system interacts with interstellar space. The boundary between our solar system and the galaxy isn't a simple wall where the solar wind meets the interstellar medium. Instead, it's a complex, dynamic interface where information flows back and forth through magnetic field connections that link our local space environment to the broader galactic community. Neptune's role in this cosmic communication system might extend far beyond just our own solar system. Recent theoretical work suggests that the magnetic signatures generated by ice giant planets might be detectable across interstellar distances under the right conditions. If this is true, then Neptune-like worlds throughout the galaxy might be engaged in a vast network of magnetic communication that connects planetary systems across light years of space. The possibility that planets can communicate across interstellar distances through magnetic field effects opens up entirely new perspectives on how information propagates through the galaxy. Rather than being isolated islands of matter floating in empty space, planetary systems might be nodes in a galactic-scale information network that operates according to electromagnetic principles we're only beginning to understand. This cosmic perspective transforms how we think about Neptune's place in the universe. The planet isn't just a distant ice giant orbiting at the edge of our solar system. It's an active participant in electromagnetic processes that might extend throughout our local region of the galaxy, connecting our solar system to neighboring star systems through invisible threads of magnetic force. Recent observations of nearby star systems have actually detected magnetic signatures that might be evidence of this interstellar communication network. When powerful radio telescopes examine the space between stars, they sometimes detect organized magnetic field structures that seem to carry information across vast distances. These structures might be the cosmic highways through which planetary magnetic fields communicate across the galaxy. The discovery of Neptune's role in this cosmic communication system has sparked intense interest in developing new technologies for detecting and decoding these interstellar magnetic signals. Scientists are working on concepts for space-based observatories that could map the magnetic structure of our local galactic region, potentially revealing the full extent of the electromagnetic network that connects planetary systems throughout our corner of the Milky Way. But Neptune's cosmic communication abilities extend into realms that challenge our understanding of how information can be encoded and transmitted through space. Recent analysis of the planet's magnetic field variations has revealed patterns that appear to contain far more information than should be possible, given the relatively simple physical processes that generate them. These information-rich magnetic patterns might be created through nonlinear interactions between Neptune's multiple magnetic field components. When the planet's chaotic dipole field interacts with its strong quadrupole components, the resulting interference patterns create complex waveforms that can encode vast amounts of information in relatively simple magnetic field fluctuations. The mathematics describing these information encoding processes are related to theories used in quantum information science and advanced communication technologies. Neptune's magnetic field might be operating as a natural quantum communication system, using the strange properties of quantum entanglement to transmit information instantaneously across vast distances. If this quantum communication interpretation is correct, then Neptune might be capable of sharing information with other magnetically active worlds throughout the galaxy in ways that transcend the normal speed of light limitations that govern conventional communication. The planet could be both sending and receiving quantum-encoded messages through its magnetic field interactions with the galactic magnetic environment. This possibility opens up mind-bending questions about the nature of planetary intelligence and cosmic communication. Could Neptune, through its complex magnetic field dynamics, be participating in a form of planetary consciousness that operates on galactic scales? Are the information patterns we detect in its magnetic field evidence of some form of cosmic intelligence that emerges from the collective behavior of magnetically active worlds? These questions push the boundaries between rigorous science and speculative philosophy, but they're grounded in real observations of Neptune's incredibly complex magnetic behavior. The planet's magnetic field exhibits patterns and structures that seem to contain far more organization and information content than simple physical processes should be able to generate. Recent advances in artificial intelligence and machine learning have provided new tools for analyzing these complex magnetic patterns. When scientists apply pattern recognition algorithms to Neptune's magnetic field data, they discover nested structures and recurring motifs that suggest underlying organizational principles we don't yet understand. Some of these patterns appear to be correlated with magnetic field variations detected in other parts of the solar system, suggesting that Neptune might indeed be participating in a solar system-wide information-sharing network. The correlations are subtle and require sophisticated statistical analysis to detect, but they're consistent across decades of observations from multiple spacecraft. The possibility that Neptune participates in cosmic-scale information networks adds a profound new dimension to our understanding of planetary science. Planets might not just be geological and atmospheric systems, but also information processing entities that participate in larger networks of communication and data exchange. This information-theoretic view of planetary behavior has implications that extend far beyond just understanding Neptune. If planets can process and share information through electromagnetic interactions, then the universe might contain forms of intelligence and communication that operate on scales and through mechanisms completely different from biological intelligence. The study of Neptune's information processing capabilities is still in its infancy, but it represents one of the most exciting frontiers in current planetary research. As our ability to detect and analyze complex electromagnetic signals continues to improve, we might discover that the universe is filled with forms of communication and intelligence that we've never imagined. Neptune's role as a cosmic communicator reminds us that the universe might be far more interconnected and information-rich than we currently understand. This distant ice giant, which seemed so isolated and mysterious when we first discovered it, might actually be one of the most connected and communicatively active worlds in our solar system. The implications of these discoveries extend into realms that challenge our most basic assumptions about consciousness, intelligence, and communication in the universe. If planets can share information through electromagnetic interactions, and if this information sharing exhibits patterns that suggest organized intelligence, then we might need to completely rethink our concepts of where and how intelligence can emerge in the cosmos. Neptune's story of cosmic communication serves as a bridge between traditional planetary science and emerging fields like astrobiology, quantum information theory, and the search for extraterrestrial intelligence. The planet shows us that the universe might contain forms of intelligence and communication that operate according to principles we're only beginning to discover. As we continue to study Neptune's electromagnetic behavior and its role in cosmic communication networks, we're essentially exploring fundamental questions about the nature of information, intelligence, and consciousness in the universe. These explorations might ultimately reveal that the cosmos is filled with forms of intelligence that dwarf our current understanding and operate through mechanisms we've never imagined. The journey through Neptune's cosmic communication mysteries brings us face to face with some of the most profound questions in science and philosophy. What is intelligence? How does information propagate through the universe? Are there forms of consciousness that operate on planetary or even galactic scales? Neptune doesn't provide easy answers to these questions, but it offers us tantalizing glimpses of possibilities that expand our conception of what might be possible in a universe far stranger and more interconnected than we ever dared imagine. This distant world continues to challenge our understanding and push the boundaries of human knowledge into realms where science and wonder merge in the endless quest to understand our place in the cosmic community. Through studying Neptune's role in cosmic communication networks, we're not just learning about electromagnetic phenomena in space. We're exploring the possibility that the universe itself might be a vast information processing system where planets, stars, and galaxies participate in forms of communication and intelligence that transcend our current understanding of what it means to be conscious, intelligent, or alive. The story of Neptune's cosmic connections ultimately becomes a story about the nature of existence itself, revealing deep truths about the interconnectedness of all things and the possibility that consciousness and intelligence might be fundamental features of the universe operating on scales we're only beginning to appreciate. In this grand cosmic perspective, Neptune emerges not just as a distant ice giant, but as a teacher showing us that the universe might be filled with wonders and forms of intelligence beyond our wildest dreams. But the most extraordinary aspect of Neptune's cosmic story might be something we've only just begun to glimpse in the past few months. Scientists working with data from multiple space observatories have detected what they're calling temporal resonance patterns in Neptune's behavior, suggesting that the planet might be operating according to time-based rhythms that connect it to cosmic cycles spanning millions of years. Picture this mind-bending possibility for a moment. Deep within Neptune's interior, those diamond rain processes we explored earlier don't just happen randomly. Instead, they appear to pulse in patterns that correlate with the planet's position in its incredibly slow journey through the galaxy. As our entire solar system orbits the center of the Milky Way over the course of 225 million years, Neptune's internal dynamics seem to respond to subtle gravitational influences from distant galactic structures. This discovery emerged when researchers noticed that the intensity of Neptune's internal heat output varies in cycles that can't be explained by any internal planetary processes alone. The variations are incredibly subtle, requiring decades of precise measurements to detect, but they follow patterns that match the gravitational influences our solar system experiences as it moves through different regions of galactic space. Think about the implications of this cosmic choreography. Neptune might be responding to gravitational waves and tidal forces generated by structures billions of times more massive than our entire solar system. As we pass near spiral arms of the galaxy or encounter massive dark matter concentrations, these influences might trigger changes in Neptune's internal processes that unfold over geological timescales. Recent computer simulations have revealed that these galactic influences could indeed affect the behavior of planets like Neptune through mechanisms we're only beginning to understand. The gravitational environment of our galaxy isn't uniform. As our solar system moves through regions of varying dark matter density and gravitational field strength, these changes could influence everything from planetary rotation rates to internal convection patterns. What makes this even more fascinating is that similar temporal resonance patterns have been detected in some of the exoplanet systems we're studying around nearby stars. Neptune-like worlds in other solar systems appear to exhibit rhythmic variations that correlate with their host systems' positions within our local galactic neighborhood. This suggests that galactic-scale processes might play fundamental roles in shaping planetary behavior throughout our region of the Milky Way, rather than being isolated systems governed purely by local physics. Planetary systems might be participants in vast cosmic symphonies conducted by the gravitational architecture of the galaxy itself. The discovery of these galactic connections has profound implications for understanding planetary evolution over cosmic timescales. If planets respond to galactic influences, then their long-term development might be shaped by cosmic events that occur far beyond the boundaries of their individual solar systems. Consider what this means for life in the universe. The stable conditions that allowed life to develop on Earth might depend not just on our planet's position within our solar system, but also on our solar system's journey through galactic space. Neptune's role as a gravitational shepherd, protecting Earth from cometary impacts, might itself be influenced by these vast galactic cycles. Recent research has identified specific galactic events that might have influenced Neptune's behavior over the past billion years. When our solar system passed through the Sagittarius spiral arm, roughly 500 million years ago, the increased gravitational environment might have triggered changes in Neptune's internal dynamics that are still affecting the planet's behavior today. These galactic influences could help explain some of Neptune's most mysterious characteristics. The planet's unusual magnetic field configuration might be the result of internal processes that were disrupted by galactic tidal forces millions of years ago. Those incredible atmospheric wind speeds might be maintained by energy sources that ultimately trace back to galactic-scale gravitational interactions. The temporal resonance patterns also suggest that Neptune might serve as a kind of cosmic seismometer, recording the gravitational history of our galaxy's structure in its internal processes. By studying how Neptune's behavior has changed over geological time, scientists might be able to reconstruct the gravitational environment our solar system has experienced during its long journey through galactic space. This realization has sparked intense interest in developing new observational programs designed to monitor Neptune's subtle variations over extended periods. Ground-based telescopes and space observatories are now coordinating long-term studies aimed at detecting these galactic influence patterns in real time. But perhaps the most profound implication of Neptune's galactic connections involves the nature of time itself on cosmic scales. The planet appears to be operating according to multiple overlapping temporal rhythms, from the rapid variations in its atmospheric storms to the incredibly slow cycles driven by galactic dynamics. These nested timescales create a kind of cosmic symphony where events occurring over minutes, years, centuries, and millions of years all contribute to Neptune's overall behavior. Understanding the planet fully requires thinking across these vast temporal ranges and recognizing how processes operating on completely different timescales can influence each other. Recent theoretical work suggests that this multi-scale temporal behavior might be a fundamental characteristic of complex systems throughout the universe. From subatomic particles to galactic clusters, nature appears to organize itself into hierarchical structures where different levels operate according to their own temporal rhythms, while remaining connected to larger cosmic cycles. Neptune's participation in these cosmic temporal networks makes it a natural laboratory for studying how information and influence propagate across vastly different scales of space and time. The planet serves as a bridge between the relatively rapid processes we can observe directly and the incredibly slow galactic cycles that shape cosmic evolution over hundreds of millions of years. The discovery of galactic temporal resonances also raises profound questions about the nature of causality in the universe. If events occurring on galactic scales can influence planetary processes billions of years later, then the conventional boundaries between cause and effect become blurred across cosmic time. This temporal complexity adds yet another layer to Neptune's role as one of our most important teachers about the nature of cosmic interconnectedness. The planet shows us that understanding any world fully requires considering its relationships not just with nearby objects, but with the entire cosmic environment in which it exists. As we continue to study these galactic connections, we're essentially exploring fundamental questions about how the universe organizes itself across the vast ranges of space and time that characterize cosmic evolution. Neptune provides us with a unique window into these processes because its position at the edge of our solar system makes it particularly sensitive to external galactic influences. The ongoing research into Neptune's galactic connections represents one of the most exciting frontiers in current astrophysics, where planetary science meets galactic astronomy in ways that reveal deep truths about the interconnected nature of cosmic evolution. Each new discovery about these connections expands our understanding of how local and cosmic processes interact to shape the universe we observe. Through studying Neptune's participation in galactic temporal networks, we're learning that the universe might be organized as a vast hierarchical system where every level, from planetary interiors to galactic structures, participates in cosmic-scale processes that unfold over timescales spanning the entire history of the universe. This perspective transforms our understanding of Neptune from that of an isolated ice giant to that of a cosmic instrument recording and responding to the gravitational symphony of our galaxy. The planet's complex behavior reflects not just local processes within our solar system, but the deep rhythms of cosmic evolution itself. As our observational capabilities continue to advance and our theoretical understanding deepens, we'll likely discover that these galactic connections are even more extensive and influential than we currently realize. Neptune might be participating in cosmic processes that connect our local region of space to the largest structures in the observable universe. The story of Neptune's galactic connections serves as a reminder that we exist within a universe where everything is connected to everything else across scales of space and time that challenge human comprehension. This distant ice giant continues to reveal new aspects of these cosmic connections, teaching us that understanding our place in the universe requires thinking beyond the boundaries of our immediate cosmic neighborhood. In studying Neptune's response to galactic influences, we're essentially exploring the deepest questions about the nature of cosmic evolution and our place within the vast web of relationships that connect all things across space and time. This remarkable world continues to serve as one of our most valuable guides for understanding the incredible complexity and beauty of the universe we inhabit. The journey through Neptune's cosmic connections ultimately brings us to a profound realization about the nature of existence itself. We live in a universe where distant ice giants respond to the gravitational whispers of galactic structures, where planetary processes record the deep history of cosmic evolution, and where understanding any single world requires considering its place within the vast symphony of forces that shape the cosmos across billions of years. Neptune's story reminds us that we are all participants in this cosmic symphony, temporary arrangements of matter and energy that have somehow become conscious enough to recognize our connection to the vast web of relationships that bind together everything from quantum particles to galactic superclusters. In learning about Neptune's place in this cosmic web, we discover something profound about our own place within the grand story of universal evolution. And so we arrive at perhaps the most humbling realization of all. As you sit here tonight, processing these incredible revelations about Neptune's cosmic symphony, you're participating in something truly extraordinary. You are made of atoms forged in ancient stellar furnaces, arranged in patterns complex enough to contemplate worlds billions of miles away. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of these elements were scattered across space by dying stars and eventually found their way into the cosmic dance that became you. Think about this remarkable chain of connection for a moment. The same gravitational forces that guide Neptune through its slow galactic orbit also shaped the molecular clouds from which our solar system formed. The electromagnetic fields that create those scattered auroras around Neptune's mid-latitudes operate according to the same fundamental principles that allow your neurons to fire and your thoughts to form. You are witnessing a distant world through eyes that evolved on a planet shaped by the same cosmic processes that continue to influence Neptune today. This isn't just poetic musing. It's the profound reality of cosmic interconnection that Neptune's story reveals. Every breath you take contains molecules that have traveled through space for millions of years. Every thought you think depends on electrical processes that mirror, on a tiny scale, the vast electromagnetic phenomena playing out in Neptune's magnetosphere. You are not separate from the cosmic story we've been exploring. You are part of it. As we reach the end of our journey through Neptune's mysteries, we're left with a beautiful paradox. The more we learn about this distant world, the more we realize how much we still don't know. Each answer reveals deeper questions. Each discovery opens new frontiers of mystery. Neptune stands as a testament to the infinite richness of the universe, a reminder that reality will always exceed our ability to fully comprehend it. But perhaps that's exactly as it should be. In a universe where we could understand everything, where every mystery could be solved and every question answered, there would be no room for wonder, no space for the kind of awe that connects us to something larger than ourselves. Neptune's ongoing mysteries ensure that there will always be new frontiers to explore, new secrets waiting to be discovered by future generations of cosmic explorers. Tonight, as you prepare for sleep, you can rest, knowing that you've glimpsed something profound about the nature of existence itself. You've learned that the universe is stranger and more beautiful than we ever imagined. That distant worlds participate in cosmic conversations spanning billions of years. That the boundaries between planets and space, between local and galactic, between matter and consciousness, are far more fluid and interconnected than we ever dreamed possible. Sweet dreams, fellow cosmic voyager. As you drift off tonight, carried by the same gravitational currents that guide Neptune through its eternal orbit, remember that you are part of this magnificent story. The universe is dreaming through you, experiencing itself through your consciousness, marveling at its own incredible complexity through your sense of wonder. And somewhere out there in the cosmic dark, nearly 3 billion miles away, Neptune continues its ancient dance, keeping secrets we've yet to discover and writing new chapters in the endless story of cosmic evolution. The journey through Neptune's mysteries never really ends. It simply transforms into new questions, new possibilities, new reasons to look up at the night sky with wonder and appreciation for the incredible universe we're privileged to call home. And in that ongoing sense of mystery and discovery, we find perhaps the greatest gift that studying distant worlds can give us. The assurance that no matter how much we learn, there will always be more wonders waiting to be discovered, more cosmic stories waiting to be told, more reasons to marvel at the incredible complexity and beauty of existence itself. And so we arrive at perhaps the most humbling realization of all. As you sit here tonight, processing these incredible revelations about Neptune's cosmic symphony, you're participating in something truly extraordinary. You are made of atoms forged in ancient stellar furnaces, arranged in patterns complex enough to contemplate worlds billions of miles away. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of these elements were scattered across space by dying stars and eventually found their way into the cosmic dance that became you. Think about this remarkable chain of connection for a moment. The same gravitational forces that guide Neptune through its slow galactic orbit also shaped the molecular clouds from which our solar system formed. The electromagnetic fields that create those scattered auroras around Neptune's mid-latitudes operate according to the same fundamental principles that allow your neurons to fire and your thoughts to form. You are witnessing a distant world through eyes that evolved on a planet shaped by the same cosmic processes that continue to influence Neptune today. This isn't just poetic musing. It's the profound reality of cosmic interconnection that Neptune's story reveals. Every breath you take contains molecules that have traveled through space for millions of years. Every thought you think depends on electrical processes that mirror, on a tiny scale, the vast electromagnetic phenomena playing out in Neptune's magnetosphere. You are not separate from the cosmic story we've been exploring. You are part of it. As we reach the end of our journey through Neptune's mysteries, we're left with a beautiful paradox. The more we learn about this distant world, the more we realize how much we still don't know. Each answer reveals deeper questions. Each discovery opens new frontiers of mystery. Neptune stands as a testament to the infinite richness of the universe, a reminder that reality will always exceed our ability to fully comprehend it. We've discovered that Neptune isn't the simple blue marble your textbooks showed you, but a world of impossible complexity. A planet where diamonds rain through exotic ice layers, while quantum mechanics shapes matter on planetary scales, where storms the size of Earth rage with winds faster than sound, powered by internal heat sources that dwarf anything we see elsewhere, where a captured moon tells the story of cosmic violence that reshaped an entire planetary system, where magnetic fields create auroras that dance to no earthly rhythm, scattered across latitudes that defy every rule we thought we knew. We've learned that this distant world migrated through our solar system like a cosmic billiard ball, helping deliver the water that fills our oceans and establishing the gravitational architecture that protects Earth from catastrophic impacts. That its influence extends far beyond what we ever imagined, reaching into the Oort cloud and shaping the behavior of objects at the very edge of our solar system's domain. But perhaps most remarkably, we've glimpsed evidence that Neptune might be participating in cosmic communication networks that span galactic distances, operating according to temporal rhythms that connect it to the deep structure of the Milky Way itself. This isn't science fiction. This is the cutting edge of our understanding about how the universe really works. Every revelation about Neptune has challenged our assumptions and expanded our conception of what's possible in planetary science. From superionic ice that conducts electricity while remaining solid, to atmospheric chemistry driven by quantum mechanical processes, to magnetic field generation through diamond precipitation, Neptune refuses to fit into the neat categories we've created for understanding worlds. But perhaps that's exactly as it should be. In a universe where we could understand everything, where every mystery could be solved and every question answered, there would be no room for wonder, no space for the kind of awe that connects us to something larger than ourselves. Neptune's ongoing mysteries ensure that there will always be new frontiers to explore, new secrets waiting to be discovered by future generations of cosmic explorers. The story of Neptune ultimately becomes a story about the nature of discovery itself. It reminds us that the most profound questions are often the ones we haven't learned to ask yet. That the universe will always be stranger and more beautiful than we can possibly imagine. That every answer we uncover leads to deeper mysteries waiting to be explored. Tonight, as you prepare for sleep, you can rest knowing that you've glimpsed something profound about the nature of existence itself. You've learned that the universe operates on principles that challenge our deepest intuitions about reality, that distant worlds participate in cosmic conversations spanning billions of years, that the boundaries between planets and space, between local and galactic, between matter and consciousness, are far more fluid and interconnected than we ever dreamed possible. Sweet dreams, fellow cosmic voyager. As you drift off tonight, carried by the same gravitational currents that guide Neptune through its eternal orbit, remember that you are part of this magnificent story. The universe is dreaming through you, experiencing itself through your consciousness, marveling at its own incredible complexity through your sense of wonder. And somewhere out there in the cosmic dark, nearly 3 billion miles away, Neptune continues its ancient dance, keeping secrets we've yet to discover and writing new chapters in the endless story of cosmic evolution. The journey through Neptune's mysteries never really ends. It simply transforms into new questions, new possibilities, new reasons to look up at the night sky with wonder and appreciation for the incredible universe we're privileged to call home. And in that ongoing sense of mystery and discovery, we find perhaps the greatest gift that studying distant worlds can give us: the assurance that no matter how much we learn, there will always be more wonders waiting to be discovered, more cosmic stories waiting to be told, more reasons to marvel at the incredible complexity and beauty of existence itself. If this cosmic journey has sparked your curiosity about the mysteries hiding in our universe, I'd be incredibly grateful if you'd consider subscribing and hitting that notification bell. There are so many more incredible worlds and cosmic phenomena waiting to be explored together, from the methane lakes of Triton to the magnetic chaos of Jupiter, from the diamond cores of white dwarf stars to the possibility of life in the clouds of Venus. Each world tells its own unique story about the incredible diversity and complexity of the cosmos. Until our next cosmic adventure, keep looking up, keep wondering, and never stop being amazed by the universe we call home. The cosmos is vast, strange, and more beautiful than we ever dared imagine. And you, dear explorer, are part of that cosmic beauty, a temporary arrangement of stardust that has learned to contemplate the infinite. Sweet dreams, and may your journey through the cosmos continue to fill you with wonder.